In this recording, I'm going to talk about the Adam Moulton methods. The Adam Moulton methods are an extension of the Bolton method, but they're implicit. In this notebook, like the other one, I'll illustrate this by looking at the initial value problem. Y dash is equal to t minus y. So, as always, read in the libraries, defining our function f t y, t minus y, discretizing our interval, such that we have step size of 0.5, and as before, we know the exact solution of this problem, so it's plotted here. Now, the Adams Moulton methods are implicit, so the general form of the two-step method is wi plus 1 is equal to wi plus h divided by 12, 5 times fti plus 1 wi plus 1, fti wi fti minus 1 wi minus 1. Now, why is it called implicit? Because we have a wi plus 1 here and a wi plus 1 here. That straight off changes the dynamic of it. It means that what we're looking for is on both sides of the equation. And also, there are three components of this equation here, but it's called a two-step method. And the reason why that is because this is not considered part of the step process, just the ti, wi, wi minus 1. So in our case, the two-step Adams Moulton is of the form wi plus 1 is equal to wi h by 12, 5 times ti plus 1 minus wi plus 1, 8 times ti wi minus ti minus 1 wi minus 1. As before, if we set I is equal to 0, we have a ti wi, a t naught w naught, and a t minus 1 wi minus 1. So our big problems here are wi minus 1 and w1. We don't know them. So we do rewrite the formula to address the wi minus 1. We rewrite the formula for I is equal to 1. So we get w2 is equal to w1 plus h divided by 12, 5 times t2 minus w2 plus 8 times t1 w1 and t0 w1. So what can we do here? Well, we can address the w1 situation by approximating that using a one-step method, or in our case here, the exact solution. But if we solve for w2, then we've solved the equation. So we rearrange this equation as it's linear to bring all the w2 things onto one side. So that means we take this term and we bring it over here. So we have w2 plus 5h divided by 12, w2, and everything here is unknown. Rearranging this, that gives us w2 is equal to w1 plus all divided by 1 plus 5 thing. So, as before, we set up our initial conditions. We need w1, which is equal to y1, needed for the method. I have to rearrange my formula to include this divided by 1 plus 5 h thing. So that means that for every single different initial value problem, I have to reorder this whole equation. But we get a very nice solution. Our local truncation error is of the form h cubed. So that means it's a third order method here, which is, in the case of the two sets Adams-Bashford, which was second order, this is a higher order method by 1, even though you're still using the same number of points. So that's great. But it does have that caveat that you have to rearrange. You see the accuracy here is 0.010402. Here we have our table of results, the Adams-Bashford, the Adams exact solution, and we see here it's really quite accurate as it goes down. But where does this fall down? So, like in the previous, if we look at the Adams Moulton, and here I'm just going to use the one-step Adams Moulton. If we look at the linear, that's no problem. That can be rearranged easily, such that wi plus 1 is equal to that. What happens here is, for something like this, the non-linear population differential equation, if we rewrite our formula, so we have wi plus 1 is equal to wih, and we have wi plus 1 minus wi squared. If we bring this over, we still have a squared term here, which we can't get rid of. This cannot be rearranged such that everything we don't know is on the left-hand side and everything we know is on the right-hand side. It's not solvable. So that's a massive problem. And that leads us into the introduction of the predictor corrected method, which I'll talk about in the next video.